what I'm going to do is I'm going to take a point charge Q, and put it in the center of a sphere. And I'll make the radius of that sphere R. Okay. All right, so we're going to calculate that's a pretty crummy sphere, but believe me, it's a sphere. We're going to calculate the electric flux out of the sphere caused by that charge in the middle. So the electric field lines from the charge are going to go like this. And so on. Okay? Now, let's see. We want to calculate the total flux. The total flux is just going to be the total of E dot A over all parts of the sphere. Okay? Let's, since this is a continuous sphere, we're actually going to set this up as a surface integral. Let's take a little bit of area here, and we'll call that area dA. It just means a little increment of area. It's a vector because we're going to define the surface vector as coming out perpendicular to that area. So we've got a little bit of area, and that has a little bit of flux coming out of it. There's going to be a small amount or an increment of flux which is just equal to the E field dot producted with dA for that little spot. Okay. And in the spirit of doing an integral, we're going to take the whole sphere and break it down into these little increments of area and then do an integration that essentially adds them all up. Well, let's see, at this particular point here, E is parallel to A, to dA, and so the cosine of the angle between them is going to be the cosine of 0 degrees, and that has a value of 1. And so we can immediately write down that d phi, the little incremental flux going through that point, is just equal to the absolute value of E times the absolute value of the area, which is dA. Excuse me. Let me write that again. D phi is just going to be equal to E, the absolute value of E, times dA. All right? So we're going to calculate the total flux for the entire sphere by just writing down that the total flux is the integration over the entire surface of the sphere of these little increments of flux d phi. All right? Well, we can take and use this expression we got here for d phi and replace it, and we're going to get the integral over the entire surface of E dot dA. Okay. All right, so for instance, we've got little d phis over here and over here. We're just going to sum over each part of that spherical surface. All right. Now, I want you to notice two things. We know from Coulomb's law that the electric field at any point is just equal to K times Q over R squared. Okay. So we know what this is. And we know that it's going out radially from the charge. Okay, so the only thing we need to know for this point is that at any point on this sphere, the electric field is the same. We know that the electric field has this spherical symmetry to it. So the electric field, the magnitude of the electric field here is equal to the magnitude of the electric field here. That's the only symmetry we have, is the spherical symmetry. So we can pull the value of the electric field out. Let me rewrite this for a minute. We get phi total is equal to the integral of the surface over the surface of the absolute value of the electric field times dA, and that's a scalar, I'm just going to write it as dA. this is a constant at any point on the surface. At any point on the surface, the angle between the electric field and the area vector is 0 degrees. And so I can rewrite this as, I can pull the electric field out of the integral, and I get the integral of dA over the surface. And if I integrate these little increments of area over the entire surface, I just get the area of the spherical surface. And so this is E times, let's see, the area on the surface of the sphere is 4 pi r squared. And then Gauss's law says this has to be equal to the charge enclosed over epsilon 0. Okay, let me erase my sphere now that I've made use of it and do the final step. If I take this part here, I get E, the absolute value of E is going to be equal to Q enclosed over 4 pi r squared epsilon 0. Remember that 4 pi epsilon 0, 1 over 4 pi epsilon 0 is equal to K, and so this is K times Q enclosed over r squared. And so we've just done the Coulomb's law derivation. We've just derived Coulomb's law as a special case of Gauss's law.